Top 20 blockchain developers interview questions and answers. Blockchain developers build decentralized applications and smart contracts that power blockchain networks. They merge coding expertise with cryptography to create secure, transparent, and efficient digital systems for the future. 1. What is blockchain technology and how does it differ from a traditional database? Blockchain is a decentralized, immutable ledger that records transactions across a distributed network of computers. Unlike traditional databases, which are controlled by a single entity and store data in centralized tables, blockchains are shared, append-only structures made of blocks, each cryptographically linked to the previous one. This structure prevents tampering and enables transparency. Traditional databases can be altered or deleted, but in a blockchain, data becomes a permanent part of the chain. This makes blockchain ideal for trustless environments, where parties need a secure, verifiable record without relying on a central authority. 2. Explain the concept of a smart contract and its role in blockchain applications. A smart contract is a self-executing program stored on the blockchain that automatically enforces the terms of an agreement once predefined conditions are met. Think of it as digital if-then logic. For example, if payment is received, then deliver the service. These contracts eliminate the need for intermediaries, reducing costs and speeding up transactions. Smart contracts power decentralized applications, dApps, enabling use cases like decentralized finance, DeFi, supply chain automation, and token sales. Their transparency and security stem from being on the blockchain, ensuring all parties can trust the outcome without needing third-party enforcement. 3. Can you describe the process of how a new block is added to the blockchain? When a transaction is initiated, it gets bundled with others into a candidate block. This block is then broadcast to a network of nodes for validation. In proof-of-work systems, miners compete to solve a complex cryptographic puzzle. The first to solve it adds the block to the chain. Once consensus is reached, the new block is permanently added, linking it to the previous one via a hash. This hash ensures immutability. Any tampering breaks the chain. The process not only secures the network but also rewards participants, e.g., miners, with cryptocurrency, incentivizing continued validation. 4. What are the key components of a transaction in a blockchain system? A blockchain transaction typically includes the sender's and receiver's public addresses, the amount transferred, a timestamp, and a digital signature. The digital signature, created with the sender's private key, proves authenticity and prevents fraud. Each transaction is hashed and included in a block along with others. Once the block is confirmed through consensus, the transaction becomes part of the immutable ledger. In more advanced blockchains, transactions may also include smart contract interactions or metadata. These components ensure the transaction is traceable, verifiable, and secure without the need for central oversight. 5. What are the advantages and disadvantages of public versus private blockchains? Public blockchains, like Ethereum or Bitcoin, are open to anyone, offering transparency, censorship resistance, and decentralization. However, they may face scalability issues and slower performance due to the need for broader consensus. Private blockchains, on the other hand, are permissioned, controlled by a known set of participants. They're faster and more scalable but lack decentralization and can be prone to central authority influence. Choosing between them depends on the use case. Public chains are great for trustless, global systems, while private chains suit enterprise applications where privacy and performance are paramount. 6. How does consensus work in a blockchain network, and what are some popular consensus algorithms? Consensus is the method blockchain networks use to agree on a single version of truth. It ensures all participants validate and record transactions honestly. Popular algorithms include proof-of-work, POW, where miners solve puzzles to add blocks, and proof-of-stake, POS, where validators are chosen based on their stake in the network. Other models like delegated proof-of-stake, DPoS, and practical Byzantine fault tolerance, PBFT, offer faster, energy-efficient consensus. Each mechanism balances security, decentralization, and scalability differently, with newer networks experimenting to find optimal trade-offs for their specific use cases. 7. What are some potential security risks or vulnerabilities in blockchain applications, and how can they be mitigated? While blockchain itself is secure, its applications can be vulnerable. Smart contracts, once deployed, can't be changed, so poor coding can lead to exploits. These risks can be mitigated through rigorous audits, formal verification, and bug bounties. Users should also use hardware wallets and multi-factor authentication. For public chains, strong consensus mechanisms prevent majority attacks. Security in blockchain is about layered defense, combining cryptographic integrity, secure coding practices, and vigilant user behavior to maintain trust and resilience. 8. Have you worked with any blockchain platforms or frameworks? Yes, I've worked with Ethereum, Hyperledger Fabric, and Polygon. On Ethereum, I developed smart contracts using Solidity for decentralized finance, DeFi, apps, and conducted thorough testing with tools like Truffle and Hardhat. With Hyperledger, I built permission networks for enterprise supply chain tracking, focusing on smart contract logic in chaincode Go. On Polygon, I scaled dApps for faster, cheaper transactions. My role often spans smart contract development, back-end integration, and deploying on testnets and mainnets. Each platform brings unique strengths, from Ethereum's robust ecosystem to Hyperledger's enterprise focus, allowing tailored solutions for different blockchain needs. 9. Explain the concept of decentralization in blockchain technology and its benefits. Decentralization means no single entity controls the blockchain. Instead, power is distributed across many nodes that maintain and verify the ledger. This structure enhances security, transparency, and resilience. There's no central point of failure, and censorship becomes nearly impossible. It empowers users to control their data, assets, and interactions directly. In finance, this enables decentralized banking. In supply chains, it builds trust among parties. The benefits include reduced corruption, greater system uptime, and open innovation. Decentralization flips traditional models, giving users more control and aligning incentives for a more equitable digital ecosystem. 10. Can you discuss any scalability challenges that blockchain networks face and propose possible solutions? Blockchain's biggest scalability challenge is balancing speed, security, and decentralization, often called the blockchain trilemma. Networks like Bitcoin and Ethereum struggle with limited transactions per second due to consensus delays and block size limits. Solutions include Layer 2 scaling, e.g., rollups, state channels, which process transactions off-chain and settle them on-chain. Sharding is another method, splitting the blockchain into smaller parts that run in parallel. Upgraded consensus algorithms like Ethereum's shift to proof-of-stake also improve efficiency. Scalability is critical for mass adoption, and solving it means blockchain can power global, real-time applications. 11. What is the role of cryptography in blockchain technology, and how does it ensure security and privacy? Cryptography is the backbone of blockchain security. It secures transactions, protects user identities, and ensures data integrity. Public key cryptography allows users to sign transactions with a private key, proving ownership without revealing their identity. Hash functions link blocks immutably. Changing any data alters the hash, instantly flagging tampering. Zero-knowledge proofs, used in some advanced blockchains, allow verification without revealing sensitive information. These cryptographic techniques enable trustless systems where no central authority is needed. In essence, cryptography transforms blockchain into a secure, transparent environment that resists fraud, hacking, and unauthorized access. 12. How do you handle the issue of data privacy in a blockchain system that stores data publicly? Blockchains are transparent by design, so handling sensitive data requires strategic solutions. One common method is to store only hashes or references to data on-chain, while the actual data remains off-chain in encrypted storage. Zero-knowledge proofs, which let users validate data without revealing it. Privacy-focused blockchains like Scash use advanced cryptography to hide transaction details entirely. For permission blockchains, access controls and encryption limit visibility to authorized participants. The goal is balance, leveraging blockchain's transparency for trust, while protecting user confidentiality and complying with data regulations like GDPR. 13. Are you familiar with token standards, such as ERC-20 and ERC-721? Can you explain the purpose and differences between them? Yes, ERC-20 and ERC-721 are Ethereum token standards that define how tokens behave on the network. ERC-20 tokens are fungible, meaning each unit is identical and interchangeable, perfect for currencies or voting rights. In contrast, ERC-721 tokens are non-fungible, representing unique assets like NFTs, non-fungible tokens. Each ERC-721 token has a unique ID and metadata, ideal for digital art, gaming items, or collectibles. These standards ensure compatibility across wallets and platforms, making development and integration easier. Understanding them is essential for building decentralized apps that interact seamlessly with Ethereum's vast ecosystem. 14. What programming languages are you proficient in that are applicable to blockchain development? For blockchain development, I'm proficient in Solidity for Ethereum smart contracts and Golang for Hyperledger Fabric chain code. I also use JavaScript and TypeScript with frameworks like Hardhat and Web3.js for front-end integration and testing. Python is another tool in my kit, useful for scripting, automation, and analytics. For back-end systems interacting with blockchain, I often work with Node.js and sometimes Rust for high-performance chains like Solana. My language toolkit allows me to contribute across the stack, from smart contract logic to full-stack DApp development, ensuring secure, efficient blockchain applications. 15. How would you explain smart contracts to a non-technical person? Can you share some practical use cases? A smart contract is like a vending machine. Insert the right amount of money, and it automatically delivers your item. No clerk needed. Similarly, a smart contract is a digital agreement that executes itself once conditions are met. It's stored on the blockchain, so no one can change it after it's deployed. For example, in real estate, a smart contract could transfer property ownership once payment is confirmed. In insurance, it could trigger payouts for flight delays. These contracts cut out middlemen, reduce costs, and add trust, making everyday transactions faster, fairer, and more transparent. 16. Can you discuss your experience with distributed systems and peer-to-peer, P2P networks? Absolutely. Blockchain itself is a distributed peer-to-peer system, so my experience spans designing decentralized architectures where no single point controls data flow. I've worked with IPFS, Interplanetary File System, to store files across nodes and integrated P2P communication protocols to sync state across dApps. In distributed systems, I focus on fault tolerance, consensus, and latency management to ensure reliability. Building on networks like Ethereum or Hyperledger means understanding how nodes interact, propagate transactions, and reach consensus, all without centralized servers. This experience helps me build systems that are resilient, scalable, and aligned with blockchain's decentralized ethos. 17. What platforms or tools do you usually use for developing, testing, and deploying smart contracts? For smart contract development, I rely on Solidity with Hardhat or Truffle for building and testing. Hardhat's local blockchain environment is great for fast iterations and debugging. I use Ganache to simulate networks and MetaMask for wallet integration during front-end testing. For deployment, I leverage Alchemy, Infura, or ThirdWeb for interacting with live Ethereum networks. For automated testing, Chai and Mocha are GoTOS. On the front end, I typically use React with Ethers.js or Web3.js. This full-stack toolchain allows seamless smart contract development, from local testing to mainnet deployment, with reliable debugging and version control. 18. Can you describe a blockchain project you've worked on? What was your role, what challenges did you face, and how did you overcome them? I worked on a DeFi lending platform built on Ethereum. My role involved writing smart contracts, integrating them with the front end, and ensuring security through audits and test coverage. One major challenge was gas optimization, reducing transaction costs without sacrificing logic. We solved this by minimizing storage operations and reusing logic with Solidity libraries. Another hurdle was educating users unfamiliar with wallets or DeFi terms, so we simplified UX with guided onboarding. Collaborating across devs, designers, and auditors, we delivered a secure, user-friendly D-app that offered real-time lending/borrowing with transparency and control over funds. 19. How do you approach securing a blockchain application? Securing a blockchain app starts with smart contract safety. I write clean, minimal code, follow best practices, and avoid known pitfalls like reentrancy or integer overflows. Every contract goes through rigorous unit testing, static analysis, and third-party audits. I use tools like MythX, Slither, and OpenZeppelin libraries for added protection. On the front end, I secure wallet interactions and guard against phishing and man-in-the-middle attacks. For back-end APIs, HTTPS and authentication protocols are enforced. I also educate users on safely interacting with dApps. Security is a continuous process, not a one-time event, requiring vigilance at every layer. 20. How do you stay current with advancements in blockchain technology? I stay updated by actively engaging with the blockchain community. I follow key influencers, developers, and protocol teams on X, Twitter, contribute to forums like Stack Exchange and Reddit, and regularly read blogs from platforms like Ethereum, Consensus, and Alchemy. I attend virtual and in-person hackathons, conferences, and webinars to network and test new ideas. I also explore new white papers and GitHub repositories to see what's being built. Tools like Dune Analytics and Token Terminal help me track real-world data trends. In this fast-moving space, continuous learning isn't optional. It's the fuel for innovation and relevance. Blockchain developers are shaping the digital future with secure, decentralized solutions. Their innovations drive transparency, trust, and transformation across industries, making them vital architects of tomorrow's technology landscape.